So I guess it's already time for session one. So I would like to reach out to Martin. So thanks for sharing this session, and the floor is yours.
All right. Welcome everyone to session one on chess and optimal play. I'm Martin Müller, also from University of Alberta. And yeah, we're running 1 minute behind schedule, so let's do it. The first paper is by Goudet, Joshi, and Cazenave. It's called Convolutional Neural Networks with Specific Kernels for Computer Chess. It's one of two papers that deal in very different ways with neural nets for chess. So, Olivier, please go ahead.
Yes. Okay. Hello. Can you hear me?
Yes.
Okay. So hello everyone. My name is Olivier Goudet, and I will present you a joint work with Bhaskar, Joshi, and Tristan Cazenave. So as you said, this work is about convolutional neural networks with specific kernels for computer chess. So first, I will remind you some background on the use of neural network for chess engines. I will then present the different network architectures we have tested, as well as the new chess kernels we have proposed. I will then talk about the characteristics of neural networks, such as the number of parameters and their latency. Finally, I'll present some results on the performance of the different networks. So first, to give some context, there was works by Silver and co-authors in 2017 and 2018 with the AlphaZero algorithm. So this work demonstrated the usefulness of using a neural network for chess. So here is a quick reminder of the principle behind the AlphaZero algorithm. So basically,
Olivier, we
yeah,
cannot see your slides. Can you share them again?
Yes, sorry. Okay. Okay, sorry. Sure. Okay, can you see it?
Yes, it's good now. Thank you.
Okay, so it's better. So the AlphaZero algorithm is basically a Monte Carlo research algorithm guided by a neural network. For each position encountered in the tree, the neural network calculates two things. So first, it calculates with the policy an evaluation of the current position, which will go backward in the tree. It also calculates with the policy head a probability that each possible move is the best move. So it helps to guide the search towards the most relevant sequences in the search tree. So more recently, there has been an open source adaptation of AlphaZero, which is called Lila Chess Zero. This was the starting point for our work. So the Lila Chess Zero source code is in two parts, actually. One part is implemented in Python using the TensorFlow library. So it enables the neural networks to be trained from the games played by Lila Chess Zero with itself. The other part of the code is used to play games with a complete algorithm. It is implemented in C++ with low-level code in CUDA for the neural network. But for this paper, we only work on the first part of the code, which corresponds to the neural network training step. So during training and inference, a chess position in Lila Chess Zero is seen as an 8x8 image with 112 channels. So I won't go too much into the details here, but overall there is one plan for each time of chess piece. In the tensor also corresponding to the current position are encoded the 7 previous positions, as well as other information such as the right to castle or not for each side, black or white. So here is the classic architecture of the neural network used in Lila Chess Zero. As you can see, the input tensor of the neural network first passes through a number of residual blocks with convolutional layers. The output of this block is then sent to three different types of network. So you have on the left the policy head, which calculates the probability of each edge move being the best. The value head also, which calculates an evaluation of the position. And normally there is also a third network which calculates the number of moves remaining in the game. But actually we haven't activated it in this work. So in this work, we only work on the red part you see on the diagram. That is to say the block used in the neural network trunk. So our objectives are twofold in this work. First, we want to compare different types of convolutional neural network architectures for the network trunk. And we also introduced new types of kernels that can be used in the convolutional layers of these networks. So now I will present the different architectures for computer chess we compare in this work. So first, a quick reminder of different convolutional layers classically used in computer vision. You can see in the left the standard convolutional layers, which is used in Lila Chess 0. Here you can see that a filter of size 3 by 3 is used. So it takes as input all the channels together of the input tensor. And there may be many output channels corresponding here to the 6 different colors. So a little to the right, we can see an example of a depthwise convolutional layer, again with the 3 by 3 filters. But in this case, each channel is processed independently, and there are as many output channels as input channels. And finally, the pointwise convolution layer corresponds simply to a standard convolution, but with a kernel of size 1 by 1. You can see it on the right. So in the standard architecture of Lila Chess 0, residual blocks are used. Each block corresponds to the succession of two convolutional layers, each time followed by a batch normalization layer on the ReLU activation function. And before the last ReLU activation, a squeeze and excitation layer is used. So in simple terms, this layer calculates positive real values that weights each output channel. And there is also a skip connection, which consists of adding the input to the output of the convolutional layers. So next, we also used in this work the mobile net architecture that had already been successfully used for the game of Go in 2020. So in this architecture, the channel number is first expanded by a coefficient of 6 with a pointwise convolution. This pointwise convolution layer is followed by a depthwise convolutional layer. And finally, the output channel number is reset to the original number with a pointwise convolution. And we also work with the convnex blocks. So this is a new architecture that was recently proposed in the computer vision domain. In this architecture, there is first of all depthwise layers with large filters of size 7 by 7. This is followed by two pointwise convolutional layers with a GLU activation function in between. So, but the real novelty in our paper was the introduction of convolutional kernels adapted for chess. So first of all, in the classic convolutional layers, there are kernels that can be, for example, of size 3 by 3 or 5 by 5, as you can see on these pictures. So here we recall that each pixel of the image used to calculate the kernel operation corresponds to a square on the chessboard. So the idea was to introduce 3 new types of kernel for chess, each corresponding to a specific move in the game of chess. So the move of the knight, the rook, and the bishop. So you may notice that each of these kernels is calculated on a grid of size 5 by 5. but actually it involves as many parameters as a kernel of size 3 by 3, since the values of only 9 squares are combined together for each type of kernel. So then we can actually combine all these three chess kernels simultaneously into a single convolutional layer, for example. So as you can see on this picture, a third of the output channel will be calculated with 9 kernels, a third with rook kernels, and the final third with bishop kernels. So the same applied for depthwise convolutional layers. The difference here is that each input plane is processed independently, and therefore each time with a different type of kernel. So now, before presenting the results themselves, I will briefly discuss the characteristics of the network. So here are some features of the neural network using residual blocks with different number of blocks, different number of filters, and each of them with kernels of size 5 by 5. So you can see that the use of chess kernels considerably reduces the number of trainable parameters. However, as you can see on this table, latency and memory remain the same in these experiments. But actually, this is due to the fact that our current implementation of chess filters is suboptimal for the moment, because indeed, to compute a chess kernel, we compute actually a complete kernel of size 5 by 5, to which we apply a mask with 0 and 1s in order to hide certain inputs. But with a low-level implementation of chess kernel, we should actually have the same computational cost as for kernels of size 3 by 3. So now this table shows the characteristics of mobile networks, so using depthwise convolutional layers. There are even fewer parameters than when using these depthwise convolutional layers than convolutional residual blocks, but the latency is slightly higher than for residual blocks. So I am now going to present the performance of these different types of network with or without the use of chess kernels. So for these experiments, we recovered a Malian game played by Lila Chess Zero against itself. We kept 80% for training and 20% for validation. And we calculated two types of metrics evaluated on the validation set, which are the policy's average accuracy and the MSC loss on the evaluation value returned by the value head. So the results are averaged over 5 training runs for each configuration. And each training session is run for 20 hours on a GPU. So here we display the results on the validation set, so after a different number of training steps. On the left, the curves corresponds to policy accuracy. On the right, this is the MSC loss for the value head. So we can see that the best results are obtained for mobile nets. You can see it with the green line, actually. And you can see also that for each type of architecture, using chess kernels improves the results. As you can see when you compare, for example, the green line with the yellow line, and also, for example, for convex, the pink line in comparison with the light blue one. So we can see that the contribution of chess kernels is particularly important in combination actually with the depthwise convolutional layers used in MobileNet and ConvNext. So to check also if the use of the chess kernel is due or not to some kind of random regularization in the convolutional layers, we also compare these chess kernels with random kernels that have exactly as many parameters as the chess kernels. So the only difference is that the activated squares are randomly chosen in these random kernels. We always keep the square in the middle, but the 8 other ones are randomly chosen. So it does not correspond to chess moves. And these experiments confirm that chess filter actually, you can see on the right, for example, the green lines is better than the blue lines with random filters. So we see that, and it's especially true for mobile net architectures. And for residual net, actually, a combination with only the rook on bishop filters work better than with the three type of filters, knight, rook, and bishop. So in conclusion, we have seen that the use of mobile nets improves the network's prediction for the game of chess, especially when the new chess kernels are used in the depthwise convolutional layers. So the use of this specific kernel shows that the use of that introducing some kind of structure related to the movement of the pieces into the neural network, so can improve its efficiency. And for future work, it will be interesting to develop a low-level implementation of the depthwise convolutional layer with chess kernels directly implemented in CUDA. And the new implementation will also enable the Lila Chess 0 engine to be played with this new architecture. So thank you for your attention. And if you have questions, you are welcome.
Yeah, thank you very much for the great presentation, Olivier. So if you have a question, please type it in the Q&A window. So use the Q&A button and also raise your hand. And I will read out the questions. And until we get a question from there, let me ask maybe an obvious question. So you did filters, specific filters for 3 of the chess types. What about the other 3, like pawns and kings and queen? Did you try to make special filters as well?
Yes, I tried, but it was not better, for example, with the queen filters. So it's why I took only these 3 types of filters. And I think it corresponds to the basic move, for example, but because for the queen filters, you can the network can combine, for example, the bishop and rook and obtain the queen. So I think with my experiment, it was enough to use these 3 types of filters.
Okay, that's interesting. Another question. So at the very end, your last words are make it play. So I did not understand, why can't you just take Lila Chess 0 and use your new network and it can play chess?
Yes, because actually, for the moment, the Lila Chess 0 code is implemented in C++ and CUDA. And this, for example, the mobile net architectures and also the chess kernel are not implemented with CUDA in this framework. So what we have to do actually is to implement it and allowing also to load all the weights that we have trained in the architecture. So but I think it's feasible, but it's just that we have to implement it in CUDA to make it work so fast.
But could you make it work slowly just for testing?
Yes, but maybe we could try, but the code is not. So we have also to yes, okay, to because actually the current code is in Python. So, but maybe we can call the Python code. But yes, maybe we can do it.
Okay, it might be too slow. All right. I don't see any question yet, so please use the Q&A to ask your questions. Other than that, I do have one more question. Did you try making like full board filters so that you can get the complete moves of each piece, not just truncated to 5 by 5?
Sorry, what did you see with?
Did you try to make very large filters that are full board so you get the complete bishop or rook moves and not just the truncated?
Yes, I tried also with 7 by 7, also at least with 7 by 7 filters, but it was not better because actually using large filters is really slow actually. So it was not very good. But I also tried, yes, with the full boards. And with, for example, like a graph convolutional neural network, where you put a link between each case for the different moves, but it was a little bit too slow also. So I think it's enough with this kind of filters, and actually, with a good implementation, it could be as fast as 3x3 standard kernels, I think. Because as you can see in the chess kernels, there is it's the same number of parameters as in the 3x3 kernel. So it's
Yes, that's a very good feature. So it's sparse.
yeah.
Okay, well, let's thank the speaker again for a great talk. Great start to the conference. You can clap.
Thank you.
All right. So now let's move on. I believe the next speaker is also here. So Olivier, maybe you can switch off the video. Thank you. So our second paper is by Omori and Tadepalli, and it's a different use of CNNs for chess. The paper is called Chess Rating Estimation from Moves and Clock Times using a CNN-LSTM. And the presenter is Michael Omori. So Michael, can you please share your screen and share your slides and start your talk?
Yeah. Hi, everyone. Thanks for the good chess presentation. So let me share my screen real quick.
We see a screen already, like with an engine, a steam engine.
Can you see my screen?
Oh, now yes, now we see the chessboard. All right, go ahead.
Okay. So yeah, I'll be talking about chess rating estimation from moves and clock times using a CNN-LSTM. Yeah, it's an interesting thing, and people have probably maybe have seen streamers try to like guess the elo from moves, and it's pretty hard. You can see from this position, the white is playing the classic scholars checkmate, and you might think it's a pretty beginner opening, and it is. But if you're just trying to guess the rating or the skill of the moves or the skill of the player who's playing the moves, it'd be pretty difficult because you've only seen a few moves so far, and you can see that even in this picture that actually the world chess champion Magnus Carlsen has even played it. So everyone from beginners to champions can play the same types of moves. So what is a rating? Rating is used for pairing players against each other in games. There's different types of rating systems, like the international chess rating systems uses FIDE rating, which is based off of a much older algorithm, which basically takes into account your rating, the opponent's rating, the result, and then the expected result. So ratings are also used for determining eligibility for scholarships. Let's say you're an up-and-coming player, and some company or organization wants to sponsor you. They usually determine it by rating. Also tournaments, if your rating is a certain level, then you can play in certain tournaments or certain sections. Ratings are used for the teams and coaching. So overall, ratings are pretty important. So the current rating system, it updates sort of slowly per game, and it's only for the entire game. In a single game, a lot can happen. Different moves can happen, and people can play good moves, people can play bad moves, but the current rating system just gives you a rating for the entire game and the outcome based off of who you played. Another one of the major problems online mostly, but also for people who have one rating and then maybe a national rating and then or a FIDE rating, and then they try to get a new rating for a new for a new nation, or maybe they make a new account, is that you got to start at square zero again, basically. Like, even if you're a really experienced player, you're maybe 2,000 on one account, but then you make a new account or you're playing for a new federation, you're going to have to start at the lowest level, which is going to introduce some problems because like if you beat other people, it's going to lower their ratings, but it maybe would lower their ratings too much. Uh, Also, another thing is that with the rating system, since it's just based off of results, it doesn't really detect anomalies. So another one of the motivations I had was nowadays there's a lot of accusations of cheating. So if like a player is playing a tournament or game, and they use a chess engine, then that's not allowed. So being able to detect that is interesting. So yeah, there's different previous works. I think Olivier mentioned AlphaZero, and yeah, that's a pretty popular one. So thankfully, I don't have to talk about that again. In 2011, one of the first papers sort of related to skill modeling, tried to determine how likely a move is based off of just your rating. And so that was using like a logistic formula, and taking into account just engine evaluations and the move that was played, and how the best evaluation is different than the move evaluation that was played. Last year, there was one paper on predicting rating using a support vector machine, and it used different features. It didn't take in the moves, but it basically took in features like how long was the game, how many moves did the player make until they castled. So if a player is making like if a player is like not castling in most of their games, then it could be a suggestion that they're not too skilled, maybe, not always. And so they broke it into 10 different rating bands, and then basically predicted the accuracy. The accuracy was 17%, so it was a bit tough. And I think, yeah, I mean, part of the reason was the way they sort of distributed the data. But yeah, they didn't open source their data, so I wasn't able to compare it. The next one was Quick Skill. It was estimation from a MOBA game, basically using a transformer, not on actual like frames of the data, but also sort of using accumulated features like how many times did one player take down another, or how many times did they get defeated. So the data I took from the open source Lichess, I took from April 2021 to July 2024. I didn't take from March just because there was like a database fire, I guess, so that sort of messed up some of the results. I took 30,000 games per month, just randomly per month. So it was 1.2 million games. And yeah, sort of similar to the last talk, I also split it into like training, validation, and test. I also tested on a puzzle difficulty competition, which was a little different. It took in the input data is a string instead. So because these days transformers are pretty common, so they sort of left it as a fence string, which was also one of the more common ways to represent a position because it can allow you to fully recreate the chess position pretty easily and compactly. And then the UCI moves, which basically is just the moves like in chess notation, like E4, E5. So for the data distribution, I just wanted to take a look at it. You can see the ratings by bins of 100 are pretty normally distributed, and most people are somewhere around like, 1,000 to 1,500. And then, yeah, one interesting thing about the data, about this online data that's not very um, sort of representative of the over-the-board tournaments is that the way it works is that they try to pair most people of a similar level. because they don't want to pair people of two different levels. So you can see that most people are, when they play each other online, are within 100 points of each other. But if you go to over the board tournaments, like open tournaments, you can, the first round, you're going to play someone who can be like 400, 500, 600 points rating difference. So the time controls that I considered were basically all of the major time controls for online chess, for standard chess. Yeah, I'm not including like other variants like giveaway, so just normal chess. So there's Ultra Bullet, which is like less than 29 seconds. Bullet chess, which people usually play like 1 or 2 minutes. Blitz chess, people usually play like 3 minutes or 5 minutes. And rapid chess, which is usually like 10-minute chess or 15-minute chess. And then classical, usually classical for online at least is depending on the like if it's Lichess or chess.com, but for Lichess it's usually like 20 minutes or 30 minutes. And then also you can also play with increments. So time, like each move, instead of your time going down, your time can go up too. So that's another thing. So I considered just two metrics, the mean absolute error, so the absolute value of the difference between the prediction and the actual player's rating at that game, and then also the mean squared error, so the difference between the prediction and squaring it. Yeah, the mean squared error is more commonly used for training just because of the nice assumption that if you model the data with the expectation that the error is normally distributed, then you can simplify that to minimizing the loss, taking the mean squared error. However, the mean squared error is more prone to outliers, which is not something that I think I particularly wanted to focus on because there's a lot of players who just their ratings can be like 3,500, but it's more because they just played a lot of games and they want a lot of rating, but it might not correlate so much to their skill level. And then yeah, mean absolute error is nice and interpretable, so I'm showing that too. So yeah, starting from the input representation, which is what's commonly used, is I don't think it was mentioned in the last talk, so I'll just go over it a bit. So I'm using a 12 by 8 by 8. So a chessboard has eight rows and 8 columns, and then 12 channels. So one channel for each piece: pawn, knight, bishop, rook, queen, king, which is 6, and then two different colors. So 6 times 2 is 12, and it'll be a 1 if there's a piece on the square. Otherwise, there's a 0. So the nice thing about this input representation is that it's pretty easy for a network to understand that these different channels correspond to different pieces. But yeah, there's also other considerations where the one downside to this is that it's pretty sparse data. So yeah, in the future, I am thinking about seeing how it would work just using one channel, and instead of just a 0 or 1, just having like a number for each piece value. So yeah, I standardized all the values. I subtract by the mean rating, and then I divide by the standard deviation. So yeah, the architecture is pretty basic. I'm taking in the 12 by 8 by 8 board. I'm use a custom convolutional neural network. It's just 4 layers. I did try increasing the layers a bit, but I didn't see improved performance. Then that goes into a bidirectional long short-term memory network. So yeah, sort of my intuition was that because chess is sort of a sequential game, it might not need to take into account like all different like future and previous time steps like you might use with a transformer. So it should be enough to just sort of look at what the previous information that you have from the hidden activations and then the current position to give an output for the rating. So the output for the rating is for both players. So one for white and then one for black. Yeah, I use the standard techniques like batch normalization. So set the mean to 0 and the variance to 1 between each layer for just the CNN and not the LSTM because there's some drift problems that would cause. Yeah, then using mean pooling just to sort of I guess reduce the number of parameters and also sort of collect the features together. Leaky ReLU, so that's if it's greater than 0, it's X the input, and if it's less than, then it's gonna be alpha X. So instead of 0, which is the normal ReLU, to sort of give it a more a smooth and also learnable function when the input is less than 0. And then yeah, finally dropout as is usually used, so dropping out some of the neurons to prevent overfitting. So in general, the mean prediction got around 346. When I did the entire network, it was at 182, and also without the clock, it did worse at 239. So clock information was definitely useful for skill, and you can see that it's also really helpful in like faster time controls, where the skill might be harder to see just from the moves, but then like clock management will become really critical for faster time controls. Yeah, this is just one example of a position where you can see black is winning, has 2 more pawns. White plays knight f5, which is a mistake because black can take the knight with the bishop. So the prediction of the rating currently was 1255, but then after the move, it goes down a bit. So yeah, in summary, I used the CNN-LSTM to estimate the chess ratings and also showed that the clock feature is really useful. And then overall, there's potential for improving the rating system and anomaly detection. Yeah, so that's it. Thanks. Any questions?
Thank you, Michael. Yes, please write your questions in the Q&A box, and I will read them for the record. Until then, let me start with a question. So at the very beginning, you mentioned that you could evaluate individual moves instead of whole games. So I was curious about that. Can you explain a little bit more? Have you tried that? Did you find like it's very inconsistent within a game, or can you tell me about this aspect?
Yeah, so right now after each move I predict a rating. But for the final prediction of the game, I do take in the entire sequence of moves in the game. But I guess the nice thing about using an LSTM is that it's very fast. So you can have like a live update of a rating because you just need to keep in the hidden activation feature of the LSTM from the previous state. And then feed that into the LSTM and the CNN again to predict for the current the new move. So yeah, it takes in the input is like a sequence of moves basically, and it can either just be one move or it can be multiple moves in a game. But like you said, it's just right now I just tested for one game, so the results are decent. I mean, 182, which is like sort of like 200 points is sort of like a bracket for a rating, but definitely I'm interested in trying to train it on multiple games because one game player might play well or they might have like a bad day, so it could be tough just to see it from one game. But I was also motivated by the application that for chess tournaments, if people are cheating, they might only cheat on one game at a time and also one move at a time. So I wanted to see, can I see the skill being played in one game and also one move at a time?
Right. I wanted the same thing. So if you can find that someone plays one move that's much, much better than their general level. And so I guess in other words, can you put an interval on each move, like what type of player would play this move, like lower end and upper end? Can you get that from your data?
I guess I'm predicting, yeah, the rating of the player after they play a move.
Okay. We do have a question in the Q&A. The first question is by Hedin Stein-Grimson. And his or her question is, can you elaborate the explanation of the performance? Did it predict the actual light chess rating of the players?
Yeah, so that's what it predicted. I guess there is some potential for noise too, I guess, game by game. I was also thinking of taking like a some type of average rating, which might be more reflective of their performance. But yeah, one of the things I was thinking is that it is based off of their Lee chess rating, and it would also be interesting to have like sort of a completely separate ranking system that's sort of independent of like Lichess and like supervised learning labels in general and just could sort of like rank moves.
Okay, thank you. There is one other, it's not really a question, then more of a comment. Ian Waters says, I thought too, cheat detection. So did you consider using the system for detecting cheaters? And if
Yeah,
yes,
that's what I want to do next, but I haven't tested it on a data set.
all right. I guess that would be the first problem, to find a data set that's labeled with where the cheaters are.
Yeah, it was sort of hard because I was initially trying to collect data on Lichess. They have like an API where I can collect accounts that get banned or accounts that don't get banned, but then I realized that I mean, I guess a high proportion of the accounts that get banned are due to cheating, but then there's a small percent that get banned because like some other reason, like maybe they said something inoffensive. So yeah, also another hard thing I was trying to figure out is that like you know, cheaters, if they cheat, they probably won't tell you that they cheated. So it's really like you don't have a really accurate like way to get a labeled data set. You can look at like experts and they'll be like, "Oh, I think this person cheated." And maybe they're right a lot of the time, but they also might be wrong some of the time and they might not catch other cheaters. So, yeah, getting
Right.
a data set's definitely tough.
Yeah. All right. Well, thanks a lot, Michael, for your presentation and for your answers.
Thank you.
Okay, let's move right along. The next speaker is Jeffrey Considine, and this looks like some really, really interesting work on compressed game solving, and it's a breakthrough in solving breakthrough, and hopefully many other games. Jeffrey. We don't hear you. Can you unmute yourself?
Okay, sorry about that. Can everyone see the slides?
Yes, it's good, and we hear
Okay,
you.
great. And thank you for the pun earlier. So I'd like to talk about compressed game solving, which is a new variation on the solving techniques we've been using so far, mostly retrograde solving, retrograde analysis. And like Martin said, I used it to solve new sizes of the game breakthrough, in particular the 5x6 set size that resisted analysis 13 years ago. So to get some background context, I wanted to start off with talking about why some people think we can't solve chess yet. I don't think ever. I think in this community, we're probably more optimistic. One of the keynotes at the end of this conference is, again, our aim solving chess. But the popular narrative is that chess is really big. Retrograde solving, trying to tackle chess, is looking at 10 to the 44 positions. That's an awful lot. And if we talk about search strategies, we can get the square root of the game tree size, but the game tree size also appears to be very big, and that's not actually smaller than the solve all the positions version. In practice, we've actually been using hybrid strategies where we solve some of the endgame with retrograde analysis, and then we search forward. But we're already at a point where the next 8-piece database for chess is really large. It's more than 10 to the 16 positions. And Ronald Demand, who built the 7-piece database, estimated the next size around 2 petabytes. Yeah, kind of big. So it's popular to say we can't solve chess because there are just too many positions. We could spend a nanosecond on each one and we wouldn't have enough time. So I don't fully agree with that. I think we can be smarter than that. So kind of poking at this popular argument, the general assumption is that when we're solving the game, we need to solve some big set of positions, and the time to solve that is going to be at least proportional to the number of positions. We have alpha beta, which solves in a square root, but that's to the game tree size, and that's still just for one position. It doesn't guarantee we're going to solve all the positions we visit. And retrograde analysis can run in time linear in the number of endgame positions that we're solving. Take some engineering. The genetic team and others have done this. And if you're doing some amount of work per position, such as writing it to disk, compressing it, this bound is tight. But is that really necessary? So I don't think that is the case. So going back in how we think about solving games, there's actually a long history of talking about doing it with sets, not positions. The paper I mentioned back in 1913, 111 years ago, was talking about how to define what would be the winning and losing sets of positions in game, particularly chess then. And if we look back at von Neumann and Morgenstern's classic book in 1945 about economics and game theory, they actually were recursively defining winning and losing sets of positions based on the ply tool. The game was forced to a win or loss for one party. And there's been other work like Ginsburg, 1996, using sets, patterns of positions to prune forward circuit algorithms. So like there is actually a history of thinking about not doing all the work per position, or at least thinking about it not per position. So what we wanted to do in this work was work more directly with sets, and in particular with some kind of compressed set representation, and try as much as possible to use sublinear compressed sizes and work only on those compressed representations and do sublinear work. This is not going to always be possible on arbitrary sets, but we like to wish that it was possible on interesting sets that come up in solving, and we empirically at least found that to be the case for Breakthrough and have hints that it's true for other games. So looking into how we would go solving with sets, the next couple slides will be pretty basic, but just walking through how we're defining a game. There'll be some set of positions in the game. I'm denoting that P. Then T could be the terminal positions of the game where there are no more moves, so the game's over. And those terminal positions can be divided into terminal positions that are won and terminal positions that are lost. And that's just coming out of the game definition. And those plus some notion of how we can move, we can recursively define sets that win or lose within more ply. So after some number of moves, the game comes to an end, and one side or the other forced to win or a loss, or forced to win or received a loss, was forced into a loss. So these are kind of the classic definitions. These are pretty close to what von Neumann and Morgenstern used, but basically like a win in I+1 ply is basically, well, the game was already won, or we can have a move into a game where the other party who moves next has lost. And similarly, we can define losses in I+1 ply as positions where it's lost already, or they can move, but they can't move into a place where the other side didn't win. So they're forced into a loss. So those are I think is pretty standard within the community. They get simpler if we're using the normal play conventions. But if we have a reverse move generator, we can define these sets. We can go into more detail on each of the individual moves for a particular move. The way we describe it is in terms of a precondition, a set of changes in the position, and a postcondition. The pre and post conditions are essentially sets where the move is legal and it can be done. And the combination of the pre and post conditions will control whether you can make the move. For example, in chess, a post condition is that you can't move and be in checkmate after you moved. And then for the changes, this can be rather broad, but the definition that we're working with is very specific in that any position on the board, if we're thinking about a board, any square that changes, the change includes both the value before and the value after. And while this is very specific and blows up our number of moves, it will interact nicely with the compression that we use. Given these definitions, or these specifications for moves, we can specify a change function that applies these moves to a set and gives us all the positions that we can move to from positions in that set using that move, and then roll that up into all the moves to 4 moves given a set where all the positions in that set can move to in the forward basis, or we can drive it in the reverse basis for a reverse move generator, which we use in solving. So in this work, we mostly use the forward generation for validation to make sure our rules were written correctly. And then for solving, we use the reverse generator. So the question you might have is, can we make small versions of these sets quickly? And the answer to that is yes. There's work by Meyer, Eichberger, and Safedine back in 2020 where they said we can write quantified Boolean formulas that tell us that whether a particular position is winning or losing. And these formulas aren't that big. Polynomial sized. I believe the latest iteration of this work is linear sized in the number of ply. So these are very small representations. But the gotcha on these representations is that you need a quantified Boolean formula solver. And quantified Boolean formulas are piece-based complete. This is not something we think we can do quickly if we have more than a few ply. So while these are very, very small representations and are proof of concept that we can compress them down a lot, they are not the most useful ones if we want to evaluate a lot of positions quickly. So instead, we used deterministic finite automata for our representation. If you come from a computer science background, this might be your least or most favorite complexity class. They're very simple. They process strings in time, linear in the length of the string. This makes them super useful for compilers. And since we'll be working with boards with a fixed number of squares on the board, we essentially have linear time in that number of squares. So it's pretty fast. Might have a discrete per square, but still pretty fast. And when we're working with deterministic finite automata and these specific kinds of rules, the move specified the way I did before, then we can prove that pretty much all of move generation is linear time in the number of automata states, the size of the DFA, except for the final union. Usually these would be quadratic time operations, but our pre and post conditions are fixed size. So it's a linear time operation. And the change operation is essentially a quick rewiring from where there was a link with one value to a link with a different value. That leaves the last union, which frankly is the most expensive empirically, but it does look linear. It doesn't seem to vary a lot based on the size of the inputs. Even if it was proven linear, it does allow constant factor growth per ply, so we're not getting some magical fix breaking all our exponential time proofs on certain games like chess. we do see exponential growth in the ply when we solve using these techniques. But these DFAs can be exponentially smaller than the sets that they represent. We don't see that shrinkage in general, but they have good compression algorithms that are essentially classic computer science results. And in practice, we see small polynomial sizes using these finite automata. So what have I implemented here? We implemented a few different games. This is most of them. NIM we did just to confirm that our solution matched the analytical solution. We implemented breakthrough, which we'll show results for. Chess was a bit of a bear to implement. This was, and the referees commented on this. It took a while to get the rules validated to the point where we're confident that they're right, but we think we have that now. We did Othello just before the preprint last year, showing that it was solved. And we did Amazons, which did not show very good compression in our testing so far. But we spent most of our time solving breakthrough once we saw that we had a lot of leverage there. So I'll show you those results now. It's been a while since we had solved a bigger board game for breakthrough. Breakthrough is this like cute little game where you take a chess or checkers board and you line up 2 rows of pawns on both sides, and then it can move forward 1 square at a time, forward to the diagonal to the sides. And it doesn't have the same fast piece reduction that we see in other games like checkers, for example. So we can't use all the retrograde analysis by the usual methods. Using the finite automata to compress, we were able to solve several new board sizes around 30 squares. The ones marked in green are all new. And the one marked in blue for 6x6, that's a work in progress. Hope to finish that soon. For the one that we did, the biggest, hardest one that we did solve, this was the 5x6 size, which had previously been attempted. There are 10 to the 13 and change reachable positions. We were able to enumerate all of these using the forward move generation in an hour and a half on a laptop. Actually, the laptop that I'm presenting on now can do that. The compression rate varies by ply. You can see this chart. The top line is the number of positions at each ply, and the bottom line is the number of states in the finite automata. To give you an idea of, all our operations are going to be proportional to that, and this is in log scale. So when the bottom line is half the height of the top line, it's the square root of the size, basically. So this gives us pretty good compression rates. We then solved backwards through these reachable positions and got a complete solution here. So this is a strong solution. We can query every position that's reachable for win-loss status. We did see a long period in the middle where it was the number of states was growing exponentially with each ply we solved backwards. Okay, I'll wrap up. We also spent a while trying to solve 6x6 and got slowed down by hitting OS limits, killing the process for thrashing, and hitting 32-bit limits on the size. As of last December, I think it had gotten to the biggest solution so far, just off the partial solution. Though I recently heard that a knowledge-based solution has done a much bigger one since then. We also did some separate backwards solving, getting almost all but 10 to the 11th positions left. Wrapping up, we argued for a more set-oriented view to solving games with an emphasis on compression, which we were able to demonstrate on relatively light hardware, this 2016 8-year-old laptop. I feel like 6x6 games are going to start getting easy. Some of them are already solved. I expect Amazons will be a holdout. I really want to try Go. And if we can get things working on chess, I hope to try and get a 10 to 20 move partial solutions and make our games engine smarter. And I really want to try some knowledge integrations. There's some parallel work by Isaac Stone, Sturdivant, and Jonathan Schaefer that got some really impressive results of a similar flavor based on knowledge. So I think I should stop there.
Right. Thanks a lot, Jeffrey. Right. So I invite people again to ask questions in the Q&A, and you can start typing while the talk is in progress. But for now, let me start asking about tools. And that has two parts. What tools did you use to build your DFAs? And did you develop any tools yourself to make DFA for games especially easier to write?
So I have a GitHub repo, which I will probably make public soon, with a C++ code base to implement this. With the exception of chess, most of these games I've implemented in an hour or two. Once the code base was built out. So I think the answer is yes. I have a code base that well, it's not nicely packaged or documented, does make trying new games in this framework relatively easy.
So there was no special software used for solving DFA specifically. You just wrote that from scratch.
Yeah, no, I made it from scratch. I spent most of the time was actually trying to optimize that implementation. But like the DFA requirements, they're acyclical and they have all the match strings are the same length. So there's a lot of specializations, and then there's very large numbers of states for the bigger solutions. So I didn't see anything that out of the box would work. I spent a good amount of time trying to make it very slim and reduce the working sets, and a generic implementation using graphs internally would not work very well. Certainly not on the machines that I was using to run the solvers.
All right, maybe one. Oh, now we're getting some questions in the Q&A. This was almost the same question I was going to ask. So Ian Waters is asking, you've given a couple of examples of games where it works well or doesn't work well. Is there a way to predict reasonably accurately in advance what any particular game will be like? How easy is it doing a new game?
Okay, so doing a new game, I think many games, like if they're relatively simple, I could, having had some practice, I could implement in a small number of hours, maybe a day if I wasn't familiar with it. Chess took a long time handling all the cases for en passant and castling and all the combinations of that. And then I restructured things to have a slightly more general graph construction to reduce the work. Amazon, so Breakthrough worked really well. Amazon's not nearly as well. It was sublinear, but only slightly. And chess looked like it was, and the forward generation was like an n to the 0.7 exponent. So I've done this with a few different kinds of compression on it, and they come out similar. My intuition on what drives the difficulty is the number of distinct kind of moves going on, and which is roughly the branching factor 2. Though Amazon seems to trigger that, even though it's lots of very similar simple moves. Well, chess was not as bad as Amazon in what I've seen so far.
All right, thanks a lot, Jeffrey. There's one more question in the Q&A by Hedin, so maybe you can type the answer there because we need to move on to our final talk for the session.
Okay.
Thank you. Thanks again for the great talk. Okay, our last talk of the session is about the paper by Neller, Llano, Goudet, and Prasad. And Todd Neller is going to talk to us about the zombie dice game in the case where I think the dice are yellow, not the zombies. So please go ahead, Todd.
Thank you very much. Can you hear me?
Yes. And we
All right.
see your slides.
Well, thank you all for joining us for our talk on optimal play of the all yellow zombie dice game. We'll talk about the rules of zombie dice, our simplification to those rules, the optimality equations for solving optimal winning play. Our solution method will visualize optimal play, and then we'll have an array of different strategies that trade off complexity versus performance, but all of the policies are human playable. So Zombie Dice is a dice game for 2 or more players, but here we only look at the 2-player version, and it's a type of Jeopardy dice game where the primary mechanic is to make roll or hold decisions. A hold decision secures your turn progress, whereas rolling risks that turn progress for potentially greater progress. These are also called push your luck games. So Zombie Dice is played with a dice cup and 13 non-standard 6-sided dice. Now, these dice have 3 icons on them. There's the brain, which is good for zombies. There's the shotgun blast, which is bad for zombies. And then there are footprint icons, which are deferred results to future rolls if a person opts. So the way that I'm going to give you a sense of the rules here is to walk you through a sample round. So green dice, I should have mentioned, green dice have a greater number of favorable brain outcomes than shotgun outcomes. Red ones, indicating danger, have more shotguns, and yellow are neutral. So in this example round, a player uses the dice cup not to roll all the dice, but to draw 3 dice at random. In this case, we have a green, and a yellow drawn, and these are rolled as footprint, shotgun. Now, shotguns and brains are set aside after a roll. 1 shotgun is set aside, and the 2 green footprints are retained. The player has no points in the form of brains set aside, and so they re-roll. To do this, they need to draw an additional die from the cup. This turns out to be green. And on the second roll, a brain, a shotgun, and a footprint is rolled. The 1 brain is set aside. Another shotgun is set aside for 2 total, and 1 footprint in a green die is retained for re-roll. Player decides to not score that 1 brain and to roll again. They draw 2 more dice to join the footprint, and 2 reds are drawn from the cup. These 3 dice are rolled, resulting in brain, shotgun, giving us a total of 4 shotguns, bringing us above the 3 shotgun threshold that ends the turn with no score. It's as if the turn doesn't happen. Yet if there was scoring in prior turns, those points are retained. Only the points, the potential points in the form of brains, are lost. So the second round, or second player in the round, I'm going to briefly describe their turn, sort of summarize. They have a much better time. They roll 2 brains in a footprint, set the 2 brains aside, another 2 brains in a footprint, now 4 total set aside. There's still no shotguns, so there's very little jeopardy. They, on the third one, roll a brain and 2 shotguns, all of which are set aside. Now they have 2 shotguns, a high jeopardy situation, and 5 brains, so they opt to hold, scoring 5 points that they will have henceforth. And that's an example round. So players are playing for a goal score of 13 points. If there is a tie when 1 or more players have 13 points, then you have additional tie-breaking rounds until there is no more tie. So the way that we have simplified this is that we are looking at a simplification where all dice are assumed to be yellow. This is the first foray into analyzing maximal winning play. There is prior work for zombie dice in maximizing expected turn score per turn, but optimizing score is not the same as optimizing winning. And so in this particular way of representing the game, we have non-terminal states represented as a 5-tuple, P, I, J, B, S, where P is the current player number, I is the current player score, J is the opponent score, B is the turn total, the number of brains set aside, and S is the number of rolled shotguns set aside. Capital P of this tuple will denote the probability of player P winning in that state under the assumption that both players will be playing so as to maximize their own expected win probability.
So we began by computing some probabilities. So first we computed the probability of any given roll on a turn, denoted by P roll of B and S. Here we're only considering B and S because the number of footprints rolled can be computed by doing 3 minus B minus S. And this probability is computed combinatorically using the number of total outcomes versus each individual outcome. So then say the player chooses to roll. There are two outcomes which are represented in the formula below for P roll. We first consider the case where they roll and the number of shotguns is below 2, in which case their turn will continue and they will have the opportunity to roll again, keeping track of how many brains and shotguns were rolled, which is represented by the part on the left-hand side of the plus sign. We also have the case where the number of shotguns is greater than or equal to 3 after the roll, in which case play will pass to the opponent and the turn totals will reset and no points will be gained. So the probability of winning from here is 1 minus the probability the opponent wins from the new game state. And the probability of winning with a hold is a bit simpler. So once the player holds, they will retain all the points they gain for the turn, and play will pass the opponent. So the probability of winning on a hold is 1 minus the probability of the opponent winning from that game state. And so therefore, the probability of winning overall is the max of whether you roll or hold. So once we have these probabilities computed, we then deal with optimality equations. So we first pre-compute P roll of B and S, since this is fixed for any roll. And then we cyclically and recursively determine the probability of winning at any given game state through value iteration. Initially, we assume some arbitrary estimates for P and plug them into the right side of the equations from before to compute a new left side of the equation, substituting these new p-values back into our list of p-values. And we continue this process until there is minimal change from iteration to iteration. And it is possible, but not probable, that the game continues infinitely if there are infinitely many ties. So to handle this case, we created an artificial upper bound for calculation. So using the optimality equations above, we created a visualization of optimal play, which is split up by first the number of shotguns rolled and second the player number. For each visualization, one axis represents the player's score, one represents the opponent's score, and one represents the number of brains. And the way to interpret these solid visualizations is, should the current game state fall within the solid, the optimal strategy is to roll, and otherwise the optimal strategy is to hold. And so in the zero shotgun case, there's little risk. So the general strategy is to just go for the goal, as represented by this stepped plane here. There's also this peak that you can see in the player one strategy, which pretty much represents the fact that player one should try to exceed their opponent by a certain margin in certain cases. And then in the terms of the tiebreaker, player one is expected to roll for a fixed value no matter what the state is, and player two is aiming to exceed their opponent's score by 1. So the one shotgun case is a bit more nuanced. The players are expected to play a bit more conservatively since there's a higher risk of rolling more than 3 shotguns and thus going over. But you can still see this kind of remnants of the go for it surface when the opposing player is significantly ahead. And the tiebreaker cases are relatively the same, with a slightly lower goal for player one. And the 2 shotgun case is much simpler. Players should be content getting any points, so the goal is to essentially hold after one brain has been rolled. The main difference is that player 2 is now attempting to match player 1 in the tiebreaker, and player 1 is only going for 1 point in the tiebreaker rounds as well.
So in the sessions, we're going to introduce a range of human playable policies with the trade-off of greater complexity for the greater win rate. So by human playable, we means the hold and roll decisions can be simply decided by mental math, and every of these policies is going to be evaluated compared to the optimal plays, with each player have the equal probability of playing first. So the table here is introduced 4 different human playable policies that we have developed, and they range from the simplest one with a modest performance to the more complex one with a more excellent performance. And let's first talk about the fixed hold policy. So this one is relatively simple. So in the case it is the second player's turn, and that if he's hold, he's gonna lose, then in this case he have to roll either way. And otherwise, the state of the game can be divided into 3 general cases. So the first case, when there's no shotgun set aside, then the current player is gonna keep rolling because they have nothing to lose. And in a case when there's 1 shotgun set aside, then the current player is gonna hold at 4 brains in their current turn. And the third case, when there are 2 shotguns set aside, then this one is much more riskier. So the player is going to try to reach 1 brain for the turn. So this policy closes the gap compared to the optimal play bar to 2.74%, and just by remembering 2 constant. Now I want to talk about my case policy. So this cases, the player performed similar to the fixed hold case policy, except for one case when there's 1 shotgun set aside. I divide it into 2 sub cases. That is when the opponent's score is greater than or equal to 8. Then the current player is going to go for the win or exceed the opponent by 3. And other than that, if the opponent's score is smaller than 8, the current player is going to hold at 4. So with an additional of a constant to the fixed hold policy, the gap compared to the optimal play is closed down to 1.33%.
Yeah, and so I'll quickly go over the policy that I developed. So we first consider the tiebreaker cases. The HRA up here represents the values that player 1 should go for based on the number of shotguns in the tiebreaker case. So if we are above the goal score and there's a tie, if the scores are even, then player 1 should hold with their appropriate turn score, and player 2 will hold when B reaches 1. If player 2 is trailing and either score is above the goal score, then player 2's goal is to either match their opponent if they have 2 shotguns and otherwise exceed by 1. And in all other cases, it is best to hold. Then we consider the cases where both players are below the goal score. So if there are no shotguns rolled yet, player 1 is going to go for either the goal or try to exceed their opponent by 9, whichever is higher. And player 2 is just going to go for the goal. If there's 1 shotgun set aside and either player has at least 10, then just go for the goal. Otherwise, the best play is to hold at 4. And if 2 shotguns are rolled, the goal is simply to hold at 1. And this yields a 1.18% difference from optimal play.
So my policy here is similar to John's previous policy. It varies in a couple different ways, but the main way that you can see with the variable E on lines 9 and 18 is that it sets different go for it thresholds for times that the game is close to ending and players take great risks. Just making a couple nuanced changes, this reduces the gap between this player and the optimal player win rate down to a mere 1%. Now, this would be a lot for a person to hold in their head, but there's no complicated math here, just quite a number of nested cases. And so we favor Minh's policy as far as a good trade-off of complexity to performance. So in the future, we hope to solve zombie dice for its full complexity with different colored dice. And then it would be interesting to compare these policies to optimal play for the full game and see how important color of dice is for the strategy of the game. In conclusion, this represents first steps towards computing optimal play for zombie dice in the form of a simplification where all dice are yellow. And we present a number of human playable strategies, and the one that is described here is relatively simple, and one would only win 1.33% less than optimal with this policy. Thank you very much.
Thank you, Todd and team. That was perfect timing. Yeah, so I invite everyone again to ask some questions in the Q&A. So let me start off with maybe the obvious question. If you want to solve the full game, how much more complex do you estimate this approach to be?
Well, I don't know because we haven't done it yet, but I would expect that while the state description will have, I forget whether it's 12 or 13 variables to describe where different colored dice are in different locations of the game, I would expect that the total number of states is not going to be so prohibitive that we can't just simply make a giant hash map to enumerate all the states and to run through our variation of value iteration to get a solution.
All right. So yeah, we have a couple minutes. So let me maybe ask. Yeah, let me ask one more question. So you said you used a version of value iteration for this game, and can you comment a little bit on that?
Yeah, sure. I'll also make a little correction here. These KOs should be BSs on this slide, but take this situation right here where we have P hold at the 5 tuple being 1 minus the probability of the other player. Now, value iteration is designed for a single agent. So this is a bit of an abuse of the Markov decision process that's assumed for value iteration, and that this is extended. The equations handle 2 players where there is no tie. We handle the switch in players, the switch in perspective in the familiar way of 1 minus the probability of the other player winning in their beginning game state. So other than that, the style of solving this is just like value iteration, where you set up your optimality equations. You start out with arbitrary estimates of probability. You put those estimates in the right-hand side of the equations, crank them through, and get better left-hand side approximations, and just continue this process until things converge. And in this case, they did converge pretty easily.
Okay, I see no other questions. So let's thank the speakers again, and close the session.
Thank you very much. And thanks to my students.
Thank you. Thank you. So we reconvene in 16 minutes for the first keynote.